Okay, here are some more properties of integration. Let's first think about what happens if we want to integrate the sum of two functions. So if we had the integral from a to b of f of x plus g of x. Well, let's draw a picture of this. If you had, let me draw a little more vertical. So let's just say we have some situation like this from a to b. And if we had f of x, let's draw f of x as some sort of curve. And let's draw, well, I could draw g of x, but what I really want to do is think about f of x plus g of x. So let me draw something else that's like that. So this first one is y equals f of x. This one is y equals f plus g, f of x plus g of x. And that kind of means the difference between them is g, right? So like think about the Riemann sum idea, right? If we had some rectangle in a Riemann sum here, it's going to look like, like this, right? If I could draw. It's going to look like that, right? That's kind of like a left, maybe a left sum rectangle. Putting that on the graph. So, but it's really just, we can think of it as the sum of two other, like there's a rectangle right here, that green rectangle, and then there's a rectangle, like an orange rectangle here. Right, and this height is g of x. This height is f of, color coordinated. I want to stay color coordinated. This height's f of x. And this is delta x. So really you're just stacking Riemann sum rectangles for f and for g. And so the area of that rectangle is going to be the sum of the areas for f and for g, right? So it's sort of like clearly if you think about this, oops. Oh my God. If you think about this as like somehow related to some sort of Riemann sum for f of x plus g of x, maybe I should, let me write this a little bit better. So if we think of this as related to some sort of sum, f of xi plus g of xi times delta x, then sort of clearly there, this, we're just kind of, each individual term we can break up. We can really rewrite this as the sum from I equals 1 to n of f of xi delta x plus g of xi delta x. And in fact, we can then break this up into, two different sums because we're just summing the same terms. Plus the sum. I'm being a little more formal about it. This is it, but you can get the idea just from that picture, right? So that this is really then going to be related back to the integral of f plus the integral of g. Right, and so there's your property right there. So basically, you can just break up integrals over sums. Okay, that one's pretty clear. A second property, well, and I probably won't even draw a picture. I'll just kind of like appeal to the same concept. If you took an integral from a to b, I switch colors in the middle of, it's impressive. Never done that before. The integral from a to b of some constant times f of x. Well, this is just like scaling the height of the Riemann sum rectangle, right? By c, or scaling the height of all the Riemann sum rectangles. So this is like, yeah, scale the height of each Riemann sum rectangle by the same constant, C. And if we're just doing that, again, it's sort of like we can factor that out of the whole Riemann sum, and it's going to be kind of the same argument I gave above without actually drawing it or writing it out, because it's the same argument, so I don't really want to belabor it too much. So there you go. You just literally pull, maybe I can just draw this even better. You just pull the constant out like that. It's just important that C is a constant here. If it was like an X or something, I couldn't pull the X out of the integral. That wouldn't make sense. That actually wouldn't make sense at all, since this thing is a number. And all of a sudden, if I pulled an X out, that would be X times a number, which would be like a variable expression, which is not a number. Anyways, so, but for constants, you can do this. So this is the property there. You know what? You can actually make boxes. No, I can't actually. That's not what I intended to do at all. I think if I draw carefully and then hold it, I can make a box. I'm holding it. It's not making a box because, of course, not. Oh, this is fun, right? Oh, there we go. Look, it turned into a box, guys. Very exciting stuff. Okay. Doesn't matter. Just having fun with notability. Okay, so that's the second property. And then the third property is, well, so another question you could ask is, well, what if I want the area between two curves? So the area, how do I find the area between f of x and g of x on the interval from a to b, you know, for a less than equal to x less than equal to b? So now let's draw a picture of this. So what's important here is it gets a little tricky if the curves cross. So let's first think about what happens if they don't cross, right? So here's a function f. Here's a function g. But let's just pick an interval where they don't cross, right? So like, let's say from here to here. So x equals a to x equals b. Right, so this is the region that we want. And well, in that case, it's again the same idea that we had before with the Riemann sum rectangles, right? You have a rectangle for f like that, and you have a rectangle for g like this. And the height of this one is g of x. And the height of this one is, well, the whole thing is f of x. And so what we really want is we want this part in between, right? We really want this rectangle. But it's pretty clear that the area of this rectangle is just f of x minus g of x times delta x. F was on top, right? Yeah, times delta x. So this is delta x right here. And so as long as, you know, f is bigger than g, so I should say if f is bigger than g on the interval, oh, what happened? Then the area between is just the integral of the difference. It's the integral of f of x minus g of x. I guess I should put like an equal sign. Equals the integral of f of x minus g of x dx. Right? Now, the problem though is if they cross, then you have it's harder, right? So like if I had, on the other hand, if you had something like, so this is just kind of the basic thing. If you know which one's on top, then it's pretty easy to find the area between the two curves. But what if we had an example of something like, I don't know, let's say F is on top here and G is on top, here, right? So this is G of X. And the purple one was F of X. And again, let's say from A to B, but let's say like A is there and B is there. Well, okay. If one was on top, it'd be nice. So what we need to do is we need to identify this point in the middle where they cross, right? This might involve some analysis of the graphs to try to figure out which one's on top. If one's on top on the Hill interval, if another one's on top, or if they cross, you need to find the point where they cross. And so here, the area, but if you really kind of wanted the area between the two curves, it's really like this area. And since we're measuring an area, I do want to think of it as a positive. Then the area between, in this case, you'd have to sort of say, well, like, so the area between, in this example, would equal the integral from A to C, and it would be what F is on top there. But then you'd have to, and then you'd switch. So from C to B, G is on top. So it'd be G of X minus F of X. So just be careful is all I'm saying. Like if you want the area between two curves. Also, sometimes it asks you for an area between two curves without telling you the interval. And there, I think of something like, let me just draw it off to the side here. Like if you had some curve like that intersecting some curve like that, then really, again, it would be about finding the 2 points of intersection and then using those as the bounds of your integration. So that's just a little side comment. Okay, I will stop.